Okay, here's video 2 of chapter 10 on gases. So what we've talked about so far is when variables are changing for a gas and figuring out how the other variables respond. We also can run into what's called the ideal gas law. And this is used when you have a set sample of a gas. So you don't have the changes. You don't have P1 and P2. You just have A pressure, A volume, A amount of moles, and A temperature. So the equation is PV inert, as I say it. So it's P times V equals N times R times T. So we're familiar with what most of these. P is pressure, V is volume, N is moles, T is temperature, and then we have this new thing, R. R is the gas constant, and it has the value of 0.0821, and the units look a little crazy. It's liters times atmosphere over moles times Kelvin. I say Latin mulk to help me remember, but of course that's not a normal way of saying this. And it also indicates the units that you have to use. So remember up last chapter, or last video, you could use whichever kind of units you wanted mostly. But here you are locked in. If you have R in the equation that you're using, then you have to use liters, you have to use atmospheres, you have to use moles, and you have to use Kelvin. Of course, moles and Kelvin were already set things, but now you've got liters and atmospheres. Okay, so here, another helpful hint is if we have 1 mole of any gas at STP, think about everything you know there. You have 1 mole, so that would go in as your N. You already know R. And if you're at standard temperature and pressure, that means temperature is 0 Celsius or 273 Kelvin, and pressure is 1 atmosphere. So does it make sense that I know everything in PV inert except for volume? If I plugged in all of those values, including 1 mole of a gas, the volume will always be 22.4 liters. You could try that out for yourself if you wanted. But what it does is gives us a helpful ratio or conversion factor even that works at STP and only at STP. So any gas, if you have 1 mole, it will have the volume of 22.4 liters. I'll show you a couple of different examples of that. So using PV inert, how many moles of ammonia are in a 5-liter gas cylinder at 18 degrees Celsius if they exert a pressure of 8.65 atmospheres? So you notice nothing's changing, and therefore we're just going to use our set PV inert, our ideal gas law equation. We are going to be using R, so we've got to use all the correct units. So my volume is already in liters, that's great. My pressure is already in atmospheres. I've got my R. My T is in Celsius, so I had to add 273 to get Kelvin. And then it's just algebra. So solving for the moles, I'm going to divide by 0.0821, divide by 291, and here is my mole amount. The next one says how many grams of NO2 are in 5.24 liter cylinder if the pressure is 1.62 atmospheres at 17 degrees Celsius. So I'm looking for grams. You'll notice PV inert does not have grams, but it has moles. And remember, if I can get to moles, I can always jump over to grams. So here, let's start plugging in. We know the P, it's already in atmospheres. We know the volume, it's already in liters, that's perfect. I'm gonna look for moles. Here's my R, constant. And then here's my temperature. I've taken 17 and added 273 to get Kelvin. Our first step is to solve for moles, so I get 0.357 moles. It's best to not round until the end, but you don't have to write down all the digits, just continue to follow them through. And then we're gonna go moles to grams, and we simply do that by going to the periodic table and finding the molar mass. So I added up 1 nitrogen, 2 oxygens, so that gave me 46.01 grams per mole. So hopefully you can tell here moles are canceling because top and bottom. You multiply these two numbers and you're left with 16.4 grams. Here, what volume will be occupied by 28.4 grams of propane at STP? Now, as soon as you see STP, you can keep in mind that you have available that ratio of 22.4 liters to 1 mole. It is not a problem if you go use PV inert. It's never a problem because if I know STP, I can put in pressure, I can put in temperature from STP. I already know R. Here, I'm gonna take grams and go to moles, so that would give me N and I could find volume. So it would be no problem to use PV inert. But really, I think it's simpler if you can remember the conversion when you're at STP. So the first thing I'm going to do is go grams to moles. That's being done by adding up the molar mass of propane. So we add up carbon and hydrogen here. I'm realizing I made a mistake here when I was adding up the molar mass. I must have looked at a different compound. When you add C3H8, you actually get a molar mass of 44.11. I'm not sure where I got this 291 from, but here let's see the process and then I'll correct it in the notes. So 28.4 grams of C3H8. Down here we go your molar mass from the periodic table, which really should be 44.11, sorry, to 1 mole. So that's grams to moles. And then we can use our conversion from moles directly to liters because of STP. So 1 mole will be 22.4 liters. And here's our answer, but that's not correct. It really should be 14.4 liters. And I'll include that in the updated notes. Sorry about that. Okay, let's see the next one. How many grams of nitrogen will be in a 1.50 liter flask at STP? Again, I'm STP, so that tells me T and B. It also tells me that I can use that ratio if I find it helpful. Nitrogen is a diatomic molecule, so we've got to remember that if he's by himself, he is N2 is his formula. This time we're starting with liters. So what I can do with liters is go to moles first using the 1 mole for 22.4 liters. That's called the molar volume, by the way, because it's the volume of 1 mole. Now I'm in moles and I can go 1 mole to grams using my molar mass. So we can multiply and divide, and here is our grams of nitrogen gas. We also can see gases come into play in balanced equations. So we can be reacting gases, producing gases, and then trying to use our stoichiometry to determine the amounts. So here we know that if we have a balanced equation like this guy right here, the coefficients always and forever can be mole-to-mole ratios. So 1 mole of C2H4 will react with 3 moles of oxygen, for example. But here's the extra thing, is if you are working with gases, this only applies to gases, and it only applies if you're at constant temperature and pressure, then these coefficients can also be very helpful conversions from liter to liter. So these can be mole-to-mole. They can also be liter to liter. So for example, this problem says 1.30 liters of ethene, C2H4, are burned completely. What volume of oxygen is required as long as there's constant T and P? Well, we know that we're starting with 1.30 liters of C2H4. And so since we have constant situation with the temperature and pressure, we can go 1 liter of C2H4 on the bottom for every 3 liters of O2 up top. The 1 and the 3 are the coefficients again. So we multiply by 3 and we know that we will need 3.90 liters of oxygen. We'll see a couple different scenarios here. This one's really similar. If we've got 240 liters of NO, who is a gas, and 155 liters of oxygen, who is a gas, how many liters of NO2, which is a gas, can be produced at constant T and P? So again, constant temperature and pressure. They're all gases, so we can use these as liter to liter ratios. This brings up a limiting reactant situation because it tells me the amount of both reactants. So it's saying if you use all 240 liters of NO and you use all 155 liters of O2, how much of the NO2 can you actually make? So here we'll just have to use the ratio for both to see the maximum amount of NO2 I can make. So I take 240 NO, I put a liter to liter ratio, which is 2 NO for every 2 NO2, which of course is really a 1-to-1 ratio. So we could make 240 liters of NO2. We look at the oxygen as the other reactant. There's 155 liters available. For every 1 liter of O2, you're going to get 2 liters of NO2. So you multiply by 2 and you get 310 liters of NO2. Remember back a few chapters ago, can I make 240 or can I make 310? Well, I can only make 240 liters. That's actually my answer, because at that moment, I'm going to be out of NO gas. So NO is my limiting reactant, and my O2 is my excess. Okay, here's another scenario that comes up, this next one. And what's a little bit different is that we have different states of matter. Everybody is not a gas here. So we've got solids, gases, and liquids. So let me remind you that PV inert, that gas law, can only apply to gases. And things like temperature and pressure, they only affect gases. So I would never really care about this temperature or pressure for anything except the gas in the situation. So here it says, what volume of CO2 gas, so that's what I'm looking for in the end. Let's go ahead and have that in mind. At 21 degrees Celsius and 781 millimeters of mercury, could be absorbed by 327 grams of lithium hydroxide. So if you just went ahead and started thinking, what do I know about PV inert for the gas? Well, looking at CO2, I do know the temperature, which is 21. I'll have to add 273, so that'll give me 294 Kelvin. I've got the pressure. I show you over here a conversion from millimeters of mercury to atmospheres, so I've got to divide by 760. Remember, that was on that first page of the notes. So we've got 1.03 as my pressure. I'm looking for volume. I always know R. I don't know moles of the gas, right? It doesn't tell me anywhere here the moles of the gas or the grams of the gas. But the other piece of information is grams of lithium hydroxide, which is a solid. So what we can do is we can take the grams of the solid that we do know, and we can always take grams and go to moles. And once we get to moles of something, remember, we can always use these coefficients like we used to and just go mole to mole in between different substances. So here, for example, we'll take the 327 grams of lithium hydroxide. We'll add up all of those pieces to get our molar mass from the periodic table, and we'll go grams to moles. And now we can hop from moles to moles. These are not both gases, so it's not liter to liter. It's just a normal mole to mole conversion. For every 2 moles of LiOH, we will use 1 mole of CO2. So I multiply everything, divide by everything, and I get 6.83 moles of CO2. I can then plug that into PV inert. We've already talked about how we were given all the other information about this gas. So we can just solve for V, and that'll tell us the amount of volume of CO2 gas that will be absorbed. I put a decimal point there to kind of go 3 sig figs. These problems will generally need to tell you number of sig figs that you'll need. But temperature turned into 3 sig figs when you went to Kelvin. The pressure was 3 and the grams were 3, so that's why I went that way. Here are several more for you to practice on your own, and the answers are provided there for you.